Alright, now that we know how to calculate Kc and set up equilibrium constant expressions, we can start to use these constants. So qualitatively, when we look at a Kc value, we can tell which side of the equilibrium is going to be favored. If our Kc value is very, very large, then we are going to have products being favored. For example, combustion reactions have huge Kc values, times 10 to the 150th or more even. But they don't have to be that huge to have our products be favored. So let's look at our ammonia reaction. So nitrogen and hydrogen making ammonia. The Kc at 25 degrees Celsius is 4.1 times 10 to the 8th. There's my Kc expression, concentration of ammonia squared, and then reactants on the bottom, nitrogen times the hydrogen concentration cubed. So if I just say I have 0.01 molar for nitrogen and hydrogen, I can find the concentration of ammonia by taking the Kc times the concentrations of the reactants and then take the square root of that. When I do that, I find the ammonia concentration to be 2 molar, which is 200 times greater than the reactant concentrations. So you can see that large value of Kc times 10 to the 8th is favoring product formation. If we have a small Kc value, then our reactants are going to be favored. And a Kc around 1 means neither is really favored. So we will have a decent amount of both reactants and products in our equilibrium mixture. The other thing we can use Kc for is to predict reaction direction. So if we're given reaction concentrations, we can calculate what's called the reaction quotient, symbolized with a capital Q. We can compare this to our Kc value, and we can decide, is the reaction going to go to the right toward forming more products, or go to the left forming more reactants as the reaction heads to equilibrium. Now the Q setup is exactly the same form as Kc, but our concentrations typically are not at equilibrium. So once we evaluate our Q value, we can compare it to Kc. If our Q is larger than Kc, that basically means the reaction's gone past equilibrium and has to come back to the left, so it's going to form more reactants. Q is smaller than Kc, the reaction still needs to go to the right to form more products until equilibrium is reached. If Q happens to be almost identical to Qc or exactly equal to, then that means our reaction is already at equilibrium. So let's look at this practice problem. We'll use our ammonia reaction. We've got a 50-liter vessel, 1 mole of nitrogen, 3 moles of hydrogen, and a half mole of ammonia are in that vessel. So which way is the reaction going to go as it heads towards equilibrium at 400 degrees Celsius? And there's my Kc. So again, my Q expression is the same as Kc. And so all I have to do is plug my concentrations in. Again, concentrations. So 1 mole of nitrogen in a 50-liter vessel is 0.02 molar. And so there are my concentrations. Again, 0.5 moles of ammonia divided by 50, so my concentration is 0.01 squared. And when I evaluate that expression, my answer comes out to be 23.1 for Q, which is way bigger than Kc. So the ammonia is going to have to decompose. The reaction is going to go left towards the reactants as it heads towards equilibrium. So that's how we can use those reaction quotient values. Even more important is calculating equilibrium concentrations. If we know the Kc value, we can calculate the concentrations of the substances at equilibrium. So here's a baby step problem. Phosphorus pentachloride, it's going to decompose, and in our equilibrium mixture we'll have PCl5, PCl3, and Cl2. So if we have a 1-liter vessel and we don't know how much PCl5 is in there, but I do know there's 0.2 moles of the PCl3 and Cl2, we can figure out that unknown. We do have to know the Kc value, so yes, the Kc is given to us, and you can see it right there, is 0.0415. So first, set up our expression. So Kc is equal to my products concentration over reactants. And now I can plug in what I do know. I know the Kc value. I know the concentrations of the products. Well, it is the concentration. Okay, again, 0.20 moles, but it is a 1 liter vessel. So that is 0.2 molar times 0.2 molar. And then I don't know my PCl5. So I just have to manipulate that equation to get my answer. So essentially 0.2 squared divided by 0.0415. And I get 0.0096 molar, but again, it's a 1 liter vessel, so I know there's 0.0096 moles of the phosphorus pentachloride. So again, very pluggy-chuggy. Here's where it gets more challenging, and we see our ice tables. Because usually we know our starting concentrations, and we want to know the concentration or molar composition at equilibrium. So here's a typical question. What is the equilibrium composition of a reaction mixture if we're going to have a half a mole of hydrogen and iodine in a 1 liter vessel at a certain temperature, so 731 Kelvin. So I know my Kc is also given to me at that temperature. So yes, we need to set up our ice table. So initially, we have 0.5 molar for my hydrogen and iodine, 0.5 moles in 1 liter, and there's no hydrogen iodide. Change, of course, comes from my coefficients, so the reactants are minus x, product plus 2x. So that means at equilibrium, I'm going to have these concentrations. 0.5 minus x for my reactants, 2x for my product. So plugging those values into my Kc expression, I know my Kc is 49.7, so my products is 2x squared, and on the bottom is 0.5 minus x squared. Luckily, the numerator and the denominator are both squared, and so what I can do to this expression is take the square root of it. When I do that, I get this, 7.05 equals 2x over 0.5 minus x. So now we can see that we can solve for x. Multiply 7.05 times the 0.5 minus x, that equals 2x, rearrange, solve. So x is 0.39 molar. Now, looking back at my equilibrium composition, my hydrogen and iodine are going to be 0.5 minus 0.39, so that's 0.11 molar. And my hydrogen iodide is going to be twice that, which is 0.78 molar. Again, it told us it was a 1 liter vessel, so that's how I know hydrogen and iodine are 0.11 moles, and the hydrogen iodide 0.78 moles. So that's a fantastic problem. Again, because both the numerator and denominator were squared, I could just take the square root of that expression. That's not always going to be the case. So we will involve our lovely friend, the quadratic equation. So our last example here involves that. Here we have our phosphorus pentachloride decomposition reaction again. And it says initially the concentration of PCl5 is 1 molar. So what is our composition at 433 Kelvin when we hit equilibrium? And there again is our equilibrium constant. So our ice table, initially, again, 1 molar PCl5, nothing for my products. Change, minus x for the PCl5, plus x for PCl3 and chlorine. And so my equilibrium values or expressions are so. So now using those and plugging into my Kc expression, I end up with this. 0.0211, my Kc, is equal to x squared over 1 minus x. So I can't just take the square root of both sides. This is when I know I'm going to have to involve my lovely friend, the quadratic equation. Yay! First, let's clean up this expression. multiply, and then set everything equal to 0 so that now we have clearly defined A, B, and C values. So again, A comes from here, this is my B, and this is my C. So now I can plug away. So negative B plus or minus the square root of B squared minus 4AC, and that's all over 2A. And we can simplify. So my 0.0211 squared is 0.0004452, and then my 4AC comes out to be negative 0.0211. And so I can simplify further. Out here, negative 0.0211 divided by 2 is 0.01055 negative, plus or minus, and then my square root cleaned up is 0.0215452. So I end up with plus or minus 0.14678. Well, negative minus that, a negative molarity doesn't make sense. So there's only one logical answer, which ends up being 0.136 molar. Now we can evaluate that with our equilibrium expression. Again, these were our values. So when x equals 0.136, at equilibrium my PCl5 is 8.64 molar, and both the PCl3 and chlorine is 0.136 molar. And again, it was initially 1 molar, meaning a 1 liter vessel. So my equilibrium molar composition, 0.864 moles of PCl5 and 0.136 moles of PCl3 and Cl2. So these notes should help you do those practice problems. And stay warm, stay safe, and see you soon.